So the next problem is, the last problem is on physical pendulum, finding the time period for a physical pendulum. Physical pendulum, you can make actually any physical object, solid physical object as pendulum actually. For example, this is a ring having radius r, right? You can just pivot at some point here and then try to oscillate. It will oscillate back and forth and you can find the time. Similarly, if you have a meter stick, you can just pivot at one end of the meter stick and then set into oscillation, right, like that, and then you can find the time period. And this is the general formula for time period for any physical pendulum: 2 pi I over mgd. That's on your formula sheet, where I is the moment of inertia about the pivot point, right? I is the moment of inertia about the pivot, because moment of inertia depends on the pivot point, and d here is the distance between the pivot point and center of mass. Okay, so in this example, in this first ring example, your d is just r, because this is the pivot point, this is the center of mass, right? So your d is just the radius. So in this case, it's half the length, right? So let's do one by one. So for a ring, what's the time period formula for a ring? It's pivoted here. So just calculating that. So time period is 2 pi I over mg. This is the general formula for time period for any physical pendulum. I is the moment of inertia about the pivot point. So which is from parallel axis theorem, is ICOM plus, if you remember from previous chapter, right, this. And so H is also D actually. Okay, this is from parallel axis theorem. Okay, now just put all the values. So ICOM is the moment of inertia about the center of mass. For a ring, moment of inertia about the center of mass is mr square, just mr square. So d in this case, like I said, d is just the radius. So it's again this. By mass g again is the total mass down here. Total mass is just m, and g and d is again r, right? That's it. So that's your period formula. So if you do that, 2 pi twice r over g should be your time period. And if you know the radius, you can just find the time period, right? It's so helpful actually. You just need to know the radius of the ring. So let's do the second part. So again, second part, your d, right, in this formula is this. The center of mass of a meter stick or any stick rod is lies at the geometrical center, which is your half the length. So first, so time period general formula is I over mgd, right? And again 2 pi, this is the moment of inertia about the pivot point, which you will have to find again using parallel axis theorem, which is I is moment of inertia of center of mass plus md square, right, and divided by mgd, and just put the value of d. So moment of inertia of the rod or stick about center of mass is given on the formula sheet is 1/12 ml square. Okay, and mass d is in this case, like I said, L over 2, but there's a square, and divided by m. These masses are same, right? Mass of the stick, and d is just L over 2, right? And that's your time period. So if you simplify that, and you will end up with, so double check that, you can check the calculation. So that's the time period formula for a meter stick or any rod when you pivot at one end of this stick. And you can experimentally verify that with this calculator one if you just put some numbers. So here's the next question on a physical pendulum. So it's asking the time period for this combined physical pendulum. So you have two, say, two measure sticks, two rods, thin rods, right, T-shaped rod. These are two separate rods, making a T-shape, right? And the pivot point is right here at the end of this rod, right? And each rod has length L, and this is given to you. Here's the center of mass of the combination. The combined center of mass lies somewhere here, and it's the distance between the center of mass and the pivot point from calculation. It will be given to you is 3/4 of the total length, and based on that, it's acting in terms of the given variables. What's the total? What's the time period formula in terms of the given variable? Okay, so remember, for any physical pendulum, the time period formula is this: 2 pi, the moment of inertia about the pivot point, right, divided by mgd square root. D is the distance between the center of mass, right, and the pivot point, which is given to you 0.75 times the L. That's given. Now our main challenge is to get the total moment of inertia, right? Total moment of inertia about the pivot point for both rods. So I'm gonna first do for the top rod, this rod, right? So that's gonna give you. So here it's pivoted at the end of the rod, so it's easy. So it's called parallel axis theorem. So moment of inertia about any pivot point is given by moment of inertia about its center of mass, which is given to you, plus this ml square, md square actually, let's say x square, where x is the distance between this center of mass and pivot point. Okay, so in this case L over 2 for the first rod. We have to find the moment of inertia for both rods and combine. So moment of inertia of the center of mass for a thin rod is 1/12 ml square plus m. So x is the distance between the center of mass and the pivot point, which is half the length for this rod, right? So half the length. So if you do that, so you're going to get 1/3 of ml square. Okay, that's for the first rod, right? And for the second rod, similarly, the moment of inertia about this point, right? So first, this is the center of mass. Moment of inertia about this, and you have to shift the axis by this distance. So this is all about shifting the axis, right? Using the parallel axis theorem. So it's moment of inertia of the second about the center of mass plus shifting the axis mx square. So this is 1/12 ml square plus m. So x is the shifting the axis. It's the distance between center of mass, which is this for the second rod, and the pivot point, and which is L, right? And then you're gonna get 13/12 ml square. That's the I2. That's the moment of inertia of the second rod about this pivot point. So what's the total moment of inertia? The total, before we put this in formula. So total moment of inertia about the pivot point for both is I1 plus I2, right? You can just combine them. So 1/3 ml square plus 13/12 ml square. So the I pivot here is going to be 17/12 ml square, and we're almost done. So back to now the period formula. Time period for this combined is 2 pi I pivot, right, divided by mgd square root, and 2 pi I pivot total is 17/12 ml square divided by so this has to be the total mass. So total mass is twice m. So that's where a lot of people get confused, because you have two rods combined, so total mass is twice m. It has to be the total mass. Okay, G and D is the distance, the combined, here D is the distance between the combined center of mass and the pivot point, which is given to you is 0.75 L. Okay, and this is whole square root. And if you do that, if you combine, and the length will cancel out, mass will cancel out, and you're gonna get something like this: 2 pi 17 over 18 L over G, right, square root. So that's what you get. So that's your final answer. This is the time period, right? The period formula for a T-shaped rod. Okay. Here's the next question, and this is the easy one. So again, you have two rods, thin rods having length L each, are combined like that. They are connected here, combined at the tip, and it's pivoted at this cone, at the knife edge. And if you just displace it by a little angle and release it, it will go, it will go simple harmonic oscillation. And it's asking what's the time period and frequency, right? Once you find the time period, you can find the frequency. So again, this is the this is really easy one, because what's the combined moment of inertia about the pivot points? So they are both are pivoted at the end. So this is just the total moment of inertia, because that's the key point. Finding the moment of inertia about this is 2 times the moment of inertia of each rod pivoted at one end, and we know it's 1/3 ml square from our previous calculation. You can do it, right? Because this is the moment of inertia of the thin rod pivoted at one end, right? So it's 2/3 ml square, and then the period is 2 pi I pivot, right? Because that's our general formula. The total mass, this has to be total mass, don't get confused, GD. Okay. But D should be given, or you can calculate or given to you. So the D is the center of mass is somewhere here. That's the center of mass. That will be given to you, or you can find geometrically. The pivot, the distance between the center of mass and this, if you do calculation, it will be L divided by 2 square root of 2. Okay. But that will be given to you. That's given to you here. It's 2 pi. Again, this is 2/3 ml square divided by total mass is twice m, because you have two rods. D is, again, this is the D. D is the distance between the total combined center of mass and the pivot point, which is L divided by 2 square root of 2. And this is whole within the square root. So this is the time period. Okay, time period, first find the time period, right? And frequency is just the time period. So find that out, and frequency is just 1 over reciprocal of the period. And if you do that, if you finish this calculation, you must get something like that. So this is the frequency. So this system will execute simple harmonic oscillation. It will oscillate simple harmonically, right? And with this much hertz, that's the hertz. It depends on length, right? It just depends on the length of the rod. So here's the next question. A physical pendulum is constructed from 4 thin rods like this, right? These are 4 thin rods, and it's constructed as a square. This is a square pendulum, and it's pivoted here. And if you displace it a little bit, from this is equilibrium position, it will execute simple harmonic motion. And then it's asking what's the time period and frequency of the oscillation. That's what it is asking. So first of all, there's some trick you have to do. So for each rod, right? So first we're gonna find the moment of inertia about each rod, about the geometrical center from here, because this is half the length, right? And so once you find the total moment of inertia of all these rods about this point, then we will shift by this distance, because this is your D, and that is going to be, so this is easy because this is L over 2, right? This is L over 2. So this has to be, this has to be what, L over 2, right? The L over square root of 2, right? If you use Pythagorean theorem. and then that's it. So first of all, the total moment of inertia. So for each rod about the geometrical center, right? The moment of inertia for each rod about the geometrical center, about this, and that's just each rod has, so moment of inertia about the center of mass plus mx square, right? So this is 1/12 ml square plus x is this, which is half of, and that's going to give you 1/3 of ml square. But since there are 4 shots identical rods, the total moment of inertia about the geometrical center, right? Geometrical center is 4 times this, right? 1/3 ml square, 4 times this. So it's 4/3 ml square. So that's the total moment of inertia about the geometrical center. Now, but since the pivot point is right here, now you have to shift the axis from here to here, right? And because using parallel axis theorem. So I pivot is I geometrical center, which we just found, plus shifting the axis by, right, d distance, and this d is actually given L over root 2. Okay, so but this mass has total mass. So this is 4/3 of ml square plus the total mass right here in this md square parallel axis theorem. That has to be total mass. Total mass is 4 times m, right? Not just m. And d is L over square root of 2 square. So that's the total moment of inertia about the pivot point in this configuration. Okay. So once you have that, so and then you can simplify that. This is gonna be 10 over 3rd ml square. Now we are almost done. So then the period of this pendulum, square pendulum, is 2 pi I pivot point divided by the total mass again. So okay, don't get G and D and square root. Right. And 2 pi I pivot, we just found 10 over 3 ml square, divide total mass is again 4m G, and D is from the center mass of the system, which is the geometrical center, to the pivot point distance, which is L over 2 square root 2 whole this thing square. Okay, that's the period, right? And you can simplify that, so there are so many things it will cancel out. And this and frequency, because it's acting, the frequency is just the inverse of the time period. And if you now simplify that, and simply in simplest form, it's gonna be 0.291 1 over 2 pi G over L. Okay, right, that's it.